Hi everyone, this is my second video. Today we will learn about quick sort, one of the most famous and efficient sorting algorithms used in data structure and algorithms. Just few minutes, we will move from understanding the core concept of sorting to learning exactly how quick sort works step by step with an example. By the end of this video, you will understand how quicksort works and why it widely used in programming. Okay, let's start. Audio Jungle. Audio Jungle. Okay, before we talk about quicksort, let's quickly revise what sorting means. Sorting is simply arranging items in specific order. For example, from smallest to largest, we can call it ascending order, or largest to smallest, we call it descending order. As example, if we have an array, say 5, 3, 8, 4, 2, after sorting in ascending order, it becomes 2, 3, 4, 5, 8. Okay, there are many sorting algorithms like bubble sort, insertion sort, and merge sort. But today our focus is on the power and efficiency of quick sort. Okay, I think you simply got an idea about sorting. Mainly, quick sort is based on a powerful algorithmic strategy called divide and conquer. In simply, this means we take one big problem, divide it into small sub-problems, solve those smaller problems independently, and then combine the results. In the context of quicksort, we divide the entire array into two sub-arrays around one strategically chosen element, which we call pivot element. Now we learn about step of sort in quicksort. There are three steps we have to follow. The first step is choose a pivot element. What is pivot element? A pivot element is the element that we choose from the array to help split the array into two parts. As pivot element, we can choose any one element in array. It can be first, last, or middle element. Okay, after choose a pivot element, now we see the second step. In second step, we partition the array. This is crucial step where we rearrange the element so all numbers smaller than the pivot are placed its to left and all greater numbers are placed to its right. The pivot is now in its final sorted position. As third and last step, we apply the same process again. We recursively call quick sort on the left subarray and the right subarray. The recursion stops when we are left with only one or zero element in the subarray, as these are inherently sorted. Okay, let's work through the example. I get an array 5, 3, 8, 4, 2. Now I pick the first element 5 as my pivot. Now I partition the array. After the process, all smaller elements 3, 4, 2 move to the left of 5 and larger element 8 move to its right. We get 3, 4, 2, 5, 8. You can see 5 is now locked in its final position. Next, we recursively apply quicksort to the left part 3, 4, 2 and the right part 8. The right part has one element, so it is already sorted. On the left, I pick 3 as a new pivot. Now I partition it Smaller element 2 move to the left and the larger element 4 move to the its right. Now I get the result 2, 3, 4. Now my all pieces are sorted. We combine them for the final sorted array 2, 3, 4, 5, 8. Look at this picture. You can imagine the pivot element acting like a fence or fulcrum. The smaller number are moved to the left side of the fence and the larger numbers are pushed to the right side. Once the pivot is in place, the fence moves on to the divide those two new smaller sub-arrays, repeating the process until the entire structure is sorted. This short video explains it better. Okay, let's look at this slide. It talks about the time and space complexity of quicksort. This table shows how fast quicksort work in different situations. First, the best case. This happens when the pivot divides the array perfectly in half each time. In this case, quicksort run really fast with a time complexity of n log n. Next one is the average case. This is what usually happens when we choose a random pivot. The performance is also n log n, which means it is still very fast and efficient. Then the worst case. This occurs when the pivot is always a bad choice, like picking the smallest or last number every time. For example, if the array is already sorted, quicksort has to make many unnecessary compositions and it becomes slower with a time complexity of n square. Finally, we have space complexity, which is log n. This means quicksort needs a small amount of extra memory for its recursive calls. Even so, is still called an in-place algorithm because it doesn't need another array to do the sorting. In simply, quicksort is very fast in most cases. That's why it's widely used. But we just have to be careful when choosing the pivot to avoid the worst case. In short, quicksort is a very powerful sorting algorithm that follows the idea of divide and conquer. It breaks a big problem into smaller parts to make sorting faster. It's one of the faster sorting methods we use in practice, with an average time complexity of n log n. Quicksort also works in place, which means it doesn't need extra memory to store another array because it's so fast and efficient. Many programming languages use quicksort or its variation in their built-in sorting functions. For example, in C languages, storing library.
Okay, that's it for now. See you soon in next video. Please subscribe and press the bell icon to get notification when a video posted. Thank you guys.